Section 7.2, Trigonometric integrals. Let's try evaluating the integral of cosine to the third x dx. Notice that your first thing to try might be u substitution, letting u equal cosine x, but this won't actually help because then du is minus sine x dx, and there is no sine in this integral at the moment. So instead, what if we tried factoring out a cosine? Then we'd have cosine squared, and then we could replace that with 1 minus sine squared, because remember, sine squared plus cosine squared is 1. And then we would have a sine in there, so maybe u substitution would work in that case. So let's try that. We will look at the integral of cosine cubed in terms of its factors, cosine squared and cosine. So sine squared plus cosine squared is 1, so cosine squared is 1 minus sine squared. So we replace that, and we keep the other cosine. And now let's try letting u equal sine. Then differentiating gives us du as cosine. So that's perfect. That'll eliminate the cosine x dx right over there. So that means that our integral is equal to the integral of 1 minus u squared du, which is u minus 1/3 u cubed plus c when we do our antiderivative. And then this is an indefinite integral, so we have to plug back in what we substituted for u. So replacing u with sine again, we get sine minus 1/3 sine cubed plus c. Okay, so let's test this real quick. If we take the derivative, we get cosine minus sine squared times cosine, which is 1 minus sine squared times cosine. Alright, so perfect. That's cosine cubed. So it looks like our general trick here, if we have an odd power of a trig function, is to try to remove enough factors of it so that we can get to an even power, and then use our trig identity, sine squared plus cosine squared is 1. So let's try that again with sine to the 5th cosine squared. So we'll rewrite this integral. We could probably use a sine squared in here. So when we pull out sine, how about we write sine to the 4th as sine squared squared? And then the cosine squared is going to stay cosine squared, and we pull out one of those signs so that it goes from sine to the 5th to sine to the 4th. So then we can use our identity again. Sine squared is 1 minus cosine squared, so we switch the other way this time. But it had to be to the 4th, so I have to keep my square over there. And we still have cosine squared and sine. Okay, let's let u equal cosine this time. So then du is equal to minus sine. So our integral, sine to the 5th cosine squared, becomes the integral of 1 minus u squared times, I'll have to square that also, almost forgot, times u squared. And then sine x dx is du, just with a minus, so we just throw in a minus du. So we pull out the minus, and that's u squared minus 2u to the 4th plus u to the 6th. And we expand our square term and then multiply it by u squared. So we take the antiderivative and we get minus u cubed over 3 minus 2 times u to the 5th over 5 plus u to the 7th over 7 plus c. So that's equal to minus 1/3 cosine cubed, because we plug cosine back in for u at the end, plus 2/5 cosine to the 5th minus 1/7 cosine to the 7th plus our arbitrary constant c. So that technique worked pretty well, assuming that we had an odd exponent on sine or cosine. We would just pull that term out to make it even. But what if we're already even and we don't have any other trig terms? So then instead of using u substitution or trying to pull stuff out, it's probably easier to use these identities, where sine squared is half of 1 minus cosine 2x, and cosine squared is half of 1 plus cosine 2x. Like notice for this one, sine squared evaluated from 0 to pi, doing that integral. Well, if we just replace sine squared with 1 minus cosine squared, then we haven't made the integral any better. Now we have to integrate cosine squared. So instead of trying to do any of that, let's just use one of these identities. We'll have the integral from 0 to pi of sine squared equal to half of the integral from 0 to pi of, I don't like how that pi came out a little bit better, of 1 minus cosine 2x dx. So all I did was use this identity, and then I took out the half. Okay, so this is the exact same thing as half of x minus half sine 2x when we do our antiderivative. So in this case, I did a little mental u substitution. You let u equal 2x, then the antiderivative of cosine is sine, but you just need that half over there, so that if you were to take the derivative again, the chain rule would make this 2 hop out in front, cancel with the half, and just leave you with cosine 2x. And this half is this half. So sometimes if you have a very simple composition of functions, it's just good to do u substitution in your head and then just test afterwards and make sure that when you take the derivative, you actually get back to where you started. So let's simplify more. We can now plug in our limits from 0 to pi. So we plug in pi first, we get pi minus half of sine of 2 pi. So that's nice. Sine of 2 pi is 0, so that'll be eliminated pretty soon. And then half of 0 minus half sine 0, so that whole entire thing is 0. So all we have left with is the half pi. Okay, so if we want to integrate sine to the 4th, again, we could, potentially try other tricks, maybe use our reduction formula from last time, but that seems like overkill because we have these half-angle identities that are pretty convenient. So let's just try using one of those. We've got sine to the 4th equal to the integral of sine squared squared. We just take out one of the squares, and that way we have a sine squared in there that we can use the identity with. So this is equal to the integral of 1 minus cosine 2x over 2, or half 1 minus cosine 2x, which is the identity written above, and that we don't forget our square. So we can expand that. We get 1/4 of the integral of 1 minus 2 cosine 2x plus cosine squared 2x dx. So that's, oh wait, we still have a square in here. So it looks like we've made some progress with our integral because we've gone from a 4th power to a square, but we need to use the other identity now. So we go back up. Cosine squared was half of 1 plus cosine 2x. So let's go and use that one. So we get 1/4 of the integral of 1 minus 2 cosine 2x plus half 1 plus cosine 4x dx. Because in this case, we were starting with 2x. So in order to use our half-angle identity, we had to go to 4x instead of just going from x to 2x. So this is 1/4 of the integral of 3 over 2 minus 2 cosine 2x plus a half cosine 4x dx. And now we can just take our antiderivative. So we get 1/4 times 3 over 2 x minus sine 2x plus 1/8 sine 4x plus c. So we finished doing a whole bunch of sine and cosine integrals. When sine and cosine, well, when one of them was odd, we would just take out one of those factors and then use our identity 1 plus, sine squared plus cosine squared is 1. So 1 minus sine squared is cosine squared, 1 minus cosine squared is sine squared, and then we'd keep going. If the powers were both even, then we would use our half-angle identity. But what if we have integrals that don't have sine and cosine? What if they have tangent and secant in them? So then we need some identities for those guys. Well, we know that the derivative of tangent is secant squared. So if we have an even power of secant, then we can just pull out some secants and we'll have a du term. Perfect. So we can let u equal tangent and then we'll be good to go. Similarly, if we have an odd power of tangent, remember the derivative of tangent is secant tangent. We can pull out one of those powers and then we'll have a square term that we can use for our identity. Remember that the identity for tangent and secant is 1 plus tangent squared is equal to secant. In other words, secant squared minus 1 is equal to tangent. So that's what we're going to be taking advantage of here. Let's do an example. We've got the integral of tangent to the 6th, secant to the 4th. And that's going to be equal to the integral of tangent to the 6th. And then, like I said, we've got an even power of secant here. So how about we pull out a secant squared? And that way we'll be able to have a derivative of tangent inside of our integral. So I rewrite secant to the 4th as secant squared times secant squared. So now this is the integral of tangent. One of the secant squareds I don't need. I only need one of them for my derivative of tangent. So I replace the other one with our identity 1 plus tangent squared. And I keep the other one. So that secant squared x dx is what I can eliminate now by letting u equal tangent. Then the derivative is equal to secant squared. So our integral becomes pretty nice, actually, at least compared to how it was before. Polynomials are always nicer than anything else. So I get u to the 6th times 1 plus u squared, and then secant squared is just du. So this is the integral of u to the 6th plus u to the 8th when I distribute my u to the 6th. Taking the antiderivative then gives me u to the 7th over 7 plus u to the 9th over 9 plus c. So I substitute back in for tangent, and I get 1/7 tan 7 plus 1/9 tan to the 9th plus c. Let's try that again. This time we have an odd power of tangent, so we'll pull out one of those tangents, and that way we'll have a secant tangent for our du term. So we do our integral. And this time in terms of theta, so it's a little bit of extra writing for me, but somehow I'll survive. So I pull out a tangent, and I end up with tangent to the 4th. And I keep my secants, most of them. I'll pull out one of those two. That way I'll have secant to the 6th. And now I have a secant tangent term. Okay, perfect. So I just need this for my du. So for the rest of it, how about I replace this tangent with secant squared minus 1. And it was to the 4th, so I have to square it. I'll keep my secant to the 6th because now everything's in terms of secant, except for my du term, secant tangent. So we'll let u equal secant this time. Then du is secant tangent, like we said. So our integral, oh wait, it wasn't x, it was theta. Okay, this was our original integral. Now that becomes the integral of u squared minus 1 squared times u to the 6th. And then this entire thing is just du. Okay, so we have a nice polynomial now, u to the 10th minus 2u to the 8th plus u to the 6th du. So that's u to the 11th over 11 minus 2 times u to the 9th over 9 plus u to the 7th over 7 plus c. And then we substitute back in. So we have 1 over 11 times secant to the 11th minus 2/9 secant to the 9th plus 1/7 secant to the 7th plus c. Well, as before, we do not always have tangent and secant terms inside. Sometimes we just have one of them. So in that case, we usually need to rely on some sort of other method. In this case, what we can try doing is we write our integral as before. So we'll take tangent cubed, and we'll write that as tangent times tangent squared. And then we know that tangent squared is secant squared minus 1. So we can write this as tangent times secant squared minus 1. So then this becomes the integral of tangent times secant squared. Well, that's easy enough, but our other integral, when we distribute the tangent, becomes just tangent, which is not as nice. Fortunately, in section 5.5, we found the integral of tangent using u substitution. We wrote it as sine over cosine, did a substitution, and we saw that it's equal to the natural log of the absolute value of secant. So that means that when we do this integral, the integral of tangent times secant squared, well, that's just the integral of tangent squared over 2, right? Because the derivative of tangent is secant squared, and then the 2 hops out in front and cancels with the 2. Our other integral is a little bit more complicated, but luckily we already computed it, and that's ln of the absolute value of secant. And then we keep our plus c. So it looks like we needed to know this. So if you don't remember it from section 5.5, you might want to go back and check out the way that we computed that, because it's good to know that the integral of tangent is natural log of secant. It's going to be a pretty similar case for this problem. We're going to try to find the integral of secant cubed. Probably going to need the integral of secant. But let's just get started. How about we let u equal secant. And we're going to need another term here then, because we still have secant squared x dx. If we take the derivative, we only have secant tangent. So it looks like we need to use integration by parts. So let's let dv equal secant squared. And that'll take care of our entire integrand. So now we can say that du is equal to secant tangent when we take the derivative, dx, and v is equal to tangent, because the integral of secant squared is tangent. So now our integral of secant cubed is equal to secant tangent, because it's u times v, minus the integral of v du, so that's the integral of secant times tangent squared. So this is equal to the integral of secant times tangent minus the integral of secant times secant squared minus 1, because that's what tangent squared is equal to. So then this is equal to secant times tangent minus the integral of secant cubed when we distribute. And then we could split our integral at the same time and get the integral of secant. So let's see, now we have to figure out what the integral of secant was, which we haven't done yet. So how about we do that off to the side? Let's get the integral of secant. Well, because I already know what the integral is, I know that I can multiply by secant plus tangent on top and secant plus tangent on the bottom, and that'll help me work out. Many times in math, if you already know what your answer is, it's easier to do your proof because you know what you might need in the proof process. In this case, it's kind of like magic. So I multiply by 1, which is secant plus tangent over secant plus tangent, so that's fine. I end up with secant squared plus secant times tangent over secant plus tangent. And now I just do a u substitution. Let u equal secant plus tangent. So then du is equal to secant tangent as a derivative for secant, and then secant squared for the derivative of tangent. So plugging all of that in, I get that the integral, do a little bit better, the integral of secant is equal to the integral of 1 over u du, which is equal to the natural log of the absolute value of u plus c. So that means that this thing is equal to ln of the absolute value of secant plus tangent plus c. So I knew to multiply by secant plus tangent because I knew that that would be my answer. So let's put this all off to the side. And let's go back to our integral. So now I know that this is secant tangent minus the integral of secant cubed plus the natural log of secant plus tangent plus c. It's kind of cool now I have a formula for the integral of secant as part of this process. So we might use that again sometime. Okay, you might say, okay, well, what about this integral secant cubed? Well, that's what we wanted to solve to begin with, and now you've evaluated secant cubed in terms of secant cubed. That's terrible. But it's not. Remember, we saw this trick before. I can just take this and add it to both sides. So I get 2 times the integral of secant cubed is equal to secant tangent plus the natural log of secant plus tangent plus c. So dividing by 2, I get that secant itself, or secant cubed itself, when I take the integral, is equal to half of secant tangent plus the natural log of the absolute value of secant plus tangent plus c. Okay, to evaluate integrals of the form sine mx cosine nx, or sine mx sine nx, or cosine mx cosine nx, by mx and nx, I mean that we have something times x, like cosine 4x cosine 10x, or sine 10x cosine 8x. Whenever we have these products of sine and cosine of some multiple of x, then we could use integration by parts if we want, but it's a lot easier to use one of these identities. So for example, for this one, I've got sine of 4x cosine 5x. So I've got sine and cosine, so I use the top identity, where a is 4x and b is 5x. So that means that my integral of sine x 4x cosine 5x dx becomes the integral of half of sine of a minus b. So that's 4x minus 5x, which is minus 1x, plus sine of a plus b, which is 4x plus 5x, which is 9x. And then I pull out my half, so I get the integral of minus sine x plus sine of 9x. Remember that sine of minus something is the same thing as minus sine something, because sine is an odd function. So we get half of cosine x minus 1/9 cosine 9x, because we do a mental u substitution over here. The antiderivative of sine of 9x is cosine 9x, and we just have to multiply by 1/9, because if we were to go backwards and take the derivative, it would cancel. And we do not forget our plus c.